All right, so what we've been doing in the course up until now is I've been trying to present a very programmatic and systematic approach to spectroscopy, but particularly to NMR spectroscopy. I've wanted to give us a small collection of tools for our toolbox and to teach us how to use those and then add to them and particularly allow us to build an appreciation. So we started in 2D NMR with TOXI and COSY, and then we are with MQC and COSY, and we learned how to use those, and then we got to appreciate how TOXI could help us in certain situations, and also how HMBC could help us put the pieces together. In the last lecture, I introduced HMQC TOXI, which helps us deal with overlap. We've also, in 1D NMR, we've learned a little bit about the theory of the techniques. We've learned about coupling. We've tried to get a deep understanding of coupling. We've had a few special topics in there. We've talked about dynamic NMR, which I thought was particularly useful and relevant. We've talked about the nuclear Overhauser effect, and we've introduced some experiments over there. Now, so I was thinking about today's lecture and really trying to think what I wanted to do, and I wanted to break away from that. There are a lot of things that I found useful over the years, or think you might find useful, that I don't want to introduce in a systematic fashion. You may not need these in your toolbox. You may need them in your toolbox. You may find 2 or 3 years from now in your project, you have a particular situation that comes up, and you reach back into the recesses of your mind or into the handouts and say, oh yeah, I recall he mentioned this in class, and now I have a problem that I can use that. So today's lecture is going to be a little different. It's going to be more fragmented. It's going to be things that I have found important, or in the case of the first two, which I haven't used myself, think you might find important. And I've given you some of my sources here, and I'll give you some more. I'll actually pull on some stuff from my own work. Can somebody send a couple of handouts over to James there? All right, so where I'd like us to start is with the issue of coupling, and we've gotten really good at analyzing multiplets, and we've also learned how to address making connectivity when you have complex spectra and when multiplets overlap. And of course, the one thing that you lose out on when multiplets overlap is often it's hard to analyze those multiplets because they end up being overlapped with another multiplet. So I wanted to mention 2 techniques that may be useful to you in your own research. You're not going to get these on the final. 2D J-resolved NMR is one technique. And the other one is E-COSY, which stands for Exclusive Correlation Spectroscopy. And I guess that's a capital O in COSY, which is exclusive and so what I'll say is both of these can help you extract J values from complex multiplets. And I just took a couple of examples from sources that I like. And the source that I like these days for modern NMR experiments, to the extent that I've now bought the book 3 times, first in the 100 and more version, then in the second edition, which was 150 more NMR experiments, and now in the 200 and more NMR experiments version, is this book here. And I'll just show you very briefly the two types of spectra here. So this is This is in that book, this is an example of a 2D J-resolved spectrum, and it's of a very simple compound. It's a two-dimensional technique, but it's a two-dimensional technique where you have, on the F1 axis, you have the H1 NMR, and on the F2, I'm sorry, on the F2 axis, and on the F1 axis, you have J. And so just so you can see this for the first time, what you have here is basically a projection of the peak like this. In other words, this peak is a quartet, and so along this axis, we see 1, 2, 3, 4. And if you want, of course, on the spectrometer, you can then go and get this out separately and basically go along this dimension, because remember, these contour lines are basically peaks coming out like this. So this is obviously not a complex spectrum. This is a very, very simple molecule, but you can see what it does to the multiplets. So for example, here we have a triplet, and you see 1 main, 2 main, and 3 main peaks. There's a little bit of artifacts here. This is the methyl. You have a doublet of doublets. You have a doublet of doublets because you've got your coupling from the methyl group to this hydrogen, and then you've got a allylic coupling over here. And so you can see your doublet of doublets here, your 4 lines, so that if you pick this up would just be a doublet of doublets here. As I said, this is a trivial molecule. You would have no need to use this technique for such a simple molecule. But where you would bring this out would be in cases where maybe you had a couple of overlapping multiplets and you really wanted to get your J values. Remember, we said J values can be very useful for dealing with stereochemistry. And so if you want to figure out, okay, do I have a 10 Hertz coupling constant? Do I have an axial-axial interaction? Do I have a 3 Hertz coupling constant? This can come out. Here you have a doublet of quartets and another doublet of quartets. That's, of course, this one is, of course, associated with this proton, where you've got a big, big trans coupling and then about a 7 Hertz coupling to the methyl. And you can see your lines. So you go 1, 2, 3, and 4 is one quartet, and 1, 2, 3, and 4 is the other quartet. And then here you have another doublet of quartets, and you can see your quartets here. So put that away in your toolbox for cases you may need it. This experiment isn't too widely used because in cases where you have really bad overlap, you're still going to have this. In other words, if I had another multiplet right on top of this, you would still end up experiencing the two of them right on top. And so unless they were a little bit separated, you wouldn't necessarily be able to solve anything. The technique, so this, I'll write, well, you have this in there, yeah. So this next one is an E-cozy, and I think that's the second one in your handout here. And I just want to show you how to interpret the technique, in part because when you look at the book for the first time, it's a little bit confusing. So they've taken another trivial compound. They've taken a slice that's not on the diagonal. So here's your diagonal. I mean, in other words, of course, what they've done is an expansion. Of course, you could take the entire spectrum. They just didn't in this particular example. I just want to show you how to interpret this. So what we're looking at is a molecule that has 3 hydrogens that are all mutually coupled to each other with different coupling constants. So, and it's also confusing. It's not a square thing. So on this axis, they've taken the region from about 3 ppm, and here they've taken the region, so from about 3 to 3.4 or 2.8 to 3.4. Here they've taken it from 3.3 to 3.9. So that encompasses all of the hydrogens. So you see one multiplet for the H3A, another multiplet for H3B, which is not on this one, and so it's a doublet of doublets, a doublet of doublets, and then another H2. And I just want to show you the cross peaks here, because it's from the cross peaks that you can extract the J's. And so do you see this pattern of the little squares here? You see the little square of 4 dots here and 4 dots here? This is giving you the, quote, active coupling. This is giving you the coupling between 3B and 2A. I'm sorry, 2. And the distance, basically any of the distances in the squares, that distance is the J value. So the distance within the square is the J value. And so that's 3 to 2B. Here, 2 to 3B. Here we have 2 to 3A. And initially it's confusing until you look and you say, oh yeah, I see 1 square here and 1 square here. Do you see that? And again, it's the distances in the squares. So it's this distance that's the J for 2 to 3A. This was the J for 2 to 3B. So you can extract very easily the J's between different protons from this type of experiment. And if you're looking and trying to assign some stereochemistry based on this, then it can be a very valuable tool to add on. Here we see the 3A to 3B coupling. And of course, this is the one that's going to have the biggest coupling because that has your geminal coupling. Geminal couplings are generally bigger, not always because they're highly variable based on hybridization, but on sp3 carbons, they're generally the biggest. And so now you see our overlapping squares here. I think what I will do is highlight the square. So we have 1 square here, and maybe what I'll do is get fancy here. Pull out a different color to highlight the other square. So from the sides of the squares, basically from putting your cursor on this dot and this dot, you can get, from that distance here, you can get the J 3A 3B. Again, maybe not so important for this very simple molecule, but more important for a more complex system. All right, so that's what I want to say about that. Now, the one that we haven't talked a lot about is chirality and using NMR spectroscopy as a tool to analyze enantiomeric purity. And of course, the thing that I've emphasized in the course is that enantiomers have identical spectra. In the absence of some source of chirality, you can't tell an R molecule from an S molecule. And yet, many times, you're doing some synthetic transformation, and you want to ask, what % EE did I generate my molecules in? Or do I have a single enantiomer, or do I have a mixture of enantiomers? And this sort of question then needs some source of chirality. And so I want to introduce 2 ideas here. We'll start off with chiral shift reagents, and then I'll talk to you about chiral derivatizing agents. And in order to talk about chiral, so I'll say they're useful for determining enantiomeric purity. And in order to talk about chiral shift reagents, I first need to introduce a different concept, and that concept is lanthanide induced shift reagents, or related concept, an earlier concept. And plain old lanthanide-induced shift reagents have largely fallen out of fashion. They were developed back when NMRs were much lower field, and overlap was a much bigger problem. When you had a 60 megahertz NMR spectrometer, very few of your multiplets were beautiful multiplets, and a lot of spectra were just overlapping heaps of junk. And the idea behind lanthanide-induced shift reagents was to add a paramagnetic Lewis acid that would coordinate to a Lewis base atom on your compound, bind to it, and paramagnetism creates its own little magnetic field, so you would create extra dispersion in the molecule that would be related to where the where the shift reagent was in relation to other protons. And the general format for these reagents, many of them were based on europium. They're lanthanides. Lanthanides have unpaired electrons, unpaired F electrons. And many of them were based on europium, some of them praseodymium and some of the others. And the general format for them was an ACAC type of ligand. ACAC is acetylacetonate. Who's seen ACAC in inorganic chemistry or coordination chemistry? Okay, so they're all based on an ACAC ligand with various types of R groups here. And so the metal is typically in the +3 coordination state, so you typically have 3 of these. And the great thing about lanthanides, they literally make like a little kind of, here's your europium, and you've got this, this, and this, and then you have a spot where your Lewis base can coordinate, because lanthanides will take basically as many ligands as you can throw around them. So 2 of the non-chiral ones, before we get to the chiral ones, 2 of the non-chiral ones that are popular, and these are, by the way, this is all in the other handout that I've given you. So I used to use fribolin. This is all taken from fribolin, but I've worked with some of these compounds myself. The fribolin book I used to use as a supplemental text, a required supplemental text for the course. I like it. There are a few really good chapters. The dynamic NMR chapter is pretty good. So this one, which has 2 tert butyl groups, ACAC has 2 methyl groups. It's acetylacetonate. This one is called DPM. And DPM is just dipivoyl methanato. And so the reagent is EUDPM3. Another one, a lot of them have fluorinated groups, and particularly the chiral shift reagents. And so this one here, again, it's an ACAC type ligand. This one has 1 tert butyl group and 1 hexafluoropropyl group. And this one is called FOD. And so the reagent is EUFOD3. And so what these reagents do is the molecule will bind to it, and then they will create a high degree of magnetic anisotropy. And you usually just add a little smidgen of the reagent. So I wanted to show that to you and then talk to you about the chiral shift reagents. So this is really a beautiful example here. So this is on page 336 of your fribolin handout. And so this is a spectrum of hexanol. Hexanol is going to look like crap at any field NMR because you've got all of these methylenes, right? You've got the alpha methylene that's going to be very dispersed even at low field. And you've got the beta methylene that's going to be at high field a little bit separated. But then you've got the gamma, delta, and epsilon methylenes that will all heap together. And this was done at low field, so the beta is on top of them. And then you've got the methyl. So this is sort of your typical long chain alkyl group. So they add a little bit of EUDPM3, and look at what happens to your spectrum. You end up binding the shift reagent. It's reversible, so you don't even need a full equivalent of shift reagent. It goes on and off rapidly on the NMR timescale. It binds to the oxygen, And then your methylenes shift down, your alpha methylene shifts down, and your beta shifts less far down, and your gamma and your delta and your epsilon and your methyl. So what's happening is there's both a distance and a geometrical relationship to the shift reagent that's resulting in shifting downfield from the paramagnetism. The further it is from, the further the protons are from the paramagnetic center, the further you end up, or the less you end up with downfield shifting. There's also an angular relationship. All right, so that's sort of the background. As I said, these have, I think they're actually a useful tool for solving overlap. But they've largely fallen out of fashion for that. But chiral shift reagents are still very useful because you can have either the two enantiomers binding with different binding constants to a chiral shift reagent, or different geometrical relationships. So regardless, what happens is the protons of the two enantiomers will separate, and so you can see a methylene for one enantiomer and a methylene for another enantiomer. It takes chirality to distinguish chirality. A chiral shift reagent makes for that chirality and that type of interaction. So, okay, so chiral shift reagents, I'm sure there are more out there, but the ones that are popular, the ones that I've used, are based on camphor. Basically, it's an aldol condensation of camphor, right? So this is the structure of camphor. Camphor has a ketone over here. It has a methyl here. It has a couple of methyls on the bridgehead. We've seen camphor before in some of the problems. It's a very common terpenoid structure. And by doing an aldol condensation, you get an acac. Here I'm not drawing this. I'll just draw it as a single resonance structure rather than a dotted arrow. But you get an acac type ligand, and then you do an aldol condensation, and you can do it with you don't do it, you buy it from Aldrich. You can do it with trifluoromethylacetaldehyde or heptafluorobutyraldehyde, heptafluorobutyraldehyde. So you can have either a trifluoromethyl group or a heptafluoropropyl group, and these are respectively called EU, and so you have three of these on a europium, just like we did with the other type of ligand, right? It's just another acac ligand. And so you have the reagents that are called EU TFC3. TFC stands for trifluoromethylcamphorato, or EU HFC3 for the heptafluoropropyl camphorato. So let me show you one of these compounds, and we'll look at this with so again, now we've got our chiral shift reagent. So before we had the alcohol, what they'll do in the next demonstration is we'll look at this with a chiral amine, with phenylethylamine. So the nitrogen has a lone pair. It's Lewis basic. It can coordinate. And I'll show you two slides there, continuing in your Freiberlin handout. So usually what you do when you work with these is you titrate in the reagent because you don't want too much reagent. If you add too much chiral shift reagent, you just broaden the spectrum and turn it to hell. Because paramagnetism induces relaxation. And so if you make for very fast relaxation, you end up with broader lines. Remember, you have to have a proton stay in one spin state for a while, for like hundreds of milliseconds, in order to have a sharp line. If your proton is flipping spin states on the order of 10 milliseconds or 30 milliseconds, your line's going to be very fat. Remember, we deliberately added paramagnetic reagent chromium acac, when we talked about the inadequate experiment, because we deliberately wanted to get those quarks and other carbons to relax a little bit faster. So you basically titrate in your shift reagent. So they start, this is pure phenethylamine. This is a single enantiomer. So this is pure, I'll say pure single enantiomer. And so then they titrate in increasing amounts of shift reagent. So just look at the methine here. And your methine, as you titrate more and more, it starts to walk downfield more and more, and at the same time broaden out. And so you basically want to get it shifted a bit, but not so much that it's all completely broad. So they did this first with material that was enantiomerically pure, and then they wanted to go ahead and see if you could distinguish two enantiomers. And so in this case, they took, this is enantio-enriched. And so in the enantio-enriched, you'll notice that the two methylenes for the two methines for the two enantiomers now, so this is phenylethylamine. And so the methines for the two enantiomers now separate out because you have this chiral shift reagent that interacts differently with the two enantiomers. And so they undergo different shifting, and you can integrate them, and they're separated. Here they do the same experiment with the racemate, and you see that the peaks are about equal in size. So this can be very useful because if you're working on a project that's, say, asymmetric catalysis, and you want to be able to go ahead and measure your enantiomeric purity, if you can work out the right system to distinguish your enantiomers, then it's as quick as taking an NMR spectrum.
So we don't have to worry about the protons on our chiral shift reagent?
So the protons in the chiral shift reagent are largely blown out of the way by its paramagnetism. But as you'll see in this graph, particularly at high concentrations, this is 1:1. You'll notice here we see, I think it's one of the methyls of your chiral shift reagent, and here's some other stuff of your camphor. So the answer is yes. You do have to worry about them. But it can be a very nice and very handy technique.
What happens when you have multiple of these sites? So let's say
You'll get multiple binding points, and if you had, say, an alcohol and an amine, it would bind primarily to the amine. And if you had like an alcohol and an ether, it would probably bind primarily to the...
like multiple hydroxyl.
Then you would have it bind to all of them, and you'd have to see if... So, I mean, chiral shift reagents are not a...
Sorry, I was asking for the achiral.
What? Oh, for an achiral shift reagent. Well, it would shift everything around. Whether or not it would help you resolve things is uncertain. One of the first things I do when I have problems with overlap, and I've done this for the class, is I'll throw the thing in deuterobenzene, because deuterobenzene creates a shift that's a diamagnetic shift from the ring current of the benzene. And so very often, if I've just got a couple of persnickety overlapping protons, very often just throwing the thing in deuterobenzene is enough to shake up the spectrum. Basically, what you're trying to do is get some change and see what works. All right, this next example here, and I'm just putting this in, it's pure self-gratuitousness. This is of very little scientific value. It happens to be the first paper I published as an undergraduate, and it was just using chiral shift reagents in a very unusual way with molecules that basically was a tight ion pair, but it was determining enantiomeric ratios in a ruthenium complex. And so what was happening was it was done in a non-coordinating solvent, and so the chiral shift reagent was coordinating through chloride to the ruthenium complex, and you could see the various protons of the ring would separate. So this is the phenanthroline ring, so you could actually see the two enantiomers. Anyway, I've had a long-standing love affair with NMR spectroscopy, and maybe it's part of where it started. All right, so enough with self-indulgence here. I'm going to come back to self-indulgence in a second. And that brownie is very good, by the way, talking self-indulgence. All right, so chirality is a real problem for NMR because, as I said, NMR is not inherently able to tell enantiomers apart. You've got to do something to distinguish among enantiomers. So the another way to go, and I'll say another way because there are lots of clever ways, including ways being developed in the Rychnovsky group right now, and that have been published out of the Rychnovsky group. But another way that's been used for a very, very long time is chiral derivatizing agents. Enantiomers do not inherently have different NMR spectra, but diastereomers do. So if you can take your enantiomer, and if you can take your enantiomer or mixture of enantiomers and get it to react with an enantiopure molecule, then you make diastereomers, and you can distinguish the two of them. And there are tons of them out there, tons of chiral derivatizing agents. I'm just going to show you two. One of them is very popular. It's been around for decades, I think since the 60s. This one is called, well, it's called Mosher's reagent is what everyone refers to it as. It's MTPA, which is methoxy trifluoromethyl phenylacetic acid. This one is the R enantiomer. People call it Mosher's acid or Mosher's reagent. And what you do is you simply prepare an ester or an amide derivative with the carboxylic acid. And what's cool is the reagent itself has two very nice handles that give sharp singlets in the NMR spectrum, a methyl that gives a sharp singlet in the H1 NMR spectrum, but even more cool, a trifluoromethyl that gives a sharp singlet in the fluorine NMR spectrum. So that's one popular one for reagents that have a nucleophilic site, for compounds that have a nucleophilic site. For things that have an electrophilic site, one popular one is R-alpha methyl benzyl isocyanate, or at least that's one way you can describe this thing. So you can buy this enantiopure from Aldrich or from Fluka. There's also a version with a naphthyl group. Isocyanates react with amines to give ureas. They react with alcohols to give carbamates. And so you can very easily react your molecule to make enantiopure, to make derivatives in which you now have a chirality in there. I'm going to show you one example from my own experience, just because it happens to be something I can draw on. It also introduces some ideas of chirality. I'll just erase over this. I guess what I'll add is this was something that worked well and was easy for me, and I like it. So now we're kind of into stuff that I like, that I think's cool, that I think you'll like too, if you come to the point in your project where you have such a problem. All right, so my particular problem and project was I was taking amino acids and developing a synthetic method for making isocyanate derivatives of these. And the problem was I couldn't tell. You get an NMR spectrum and the stuff looks great, But what you couldn't tell is, are you also getting the enantiomer? In other words, is there racemization in the reaction? So I'll put a big question mark here. So in this case, it's kind of the antithesis of the isocyanate being in the molecule that of interest, being in the derivatizing agent. Here, the molecule we were making had an isocyanate in it, so I just derivatized it by reacting it with methylbenzylamine. And so, as I said, you can get methylbenzylamine as a single enantiomer. I happen to take the R enantiomer here. So we treated it with that. And the idea was to see if we were forming diastereomers. And so you could look at the diastereomers by NMR and say, OK, are we seeing any evidence of the diastereomer? And so this is what you'd get from the compound with the natural stereochemistry. And so the question is, are we getting any of the diastereomer? So when we took an NMR spectrum, we didn't see it. Now, the big problem with a negative result, of course, is you get a negative result. That doesn't prove it's not present. Maybe the diastereomer was coincident. So the way you have to address this, and this would apply to whether you're doing chiral HPLC or anything else, or chiral GC, is you need to prepare an authentic sample. So there's an easy way and a hard way to do that. So the hard way to prepare an authentic sample is to now go ahead and take the enantiomer of the amino acid and react it with this amine, with the R amine. The easy way to do this was simply to go ahead and take the enantiomer of the amine and react it with the product. That's a phenyl. Oops, this should be a phenyl here. Phenyl here. And so the point is that these two molecules are enantiomers. And so the spectrum of this molecule is identical to the spectrum of the diastereomer. So now, when you go ahead and you take this molecule here and you don't see any diastereomer, what you do to confirm that there's no diastereomer is you spike with this stuff here, and you can see if it shows up as a separate peak. And indeed it did. The methoxy of the two ends up being separated by 0.2, depending 0.02 to 0.03 ppm, which is ample. It becomes like an HPLC trace, which was ample to distinguish. And in fact, with a very small spike, with a spike of just 0.5%, you see it. So that means that we know that the original is greater than 99% EE. So no racemization to speak of. All right, so that's what I want to add about chirality and NMR and how NMR can be a useful tool. And I think what I want to do at this point is toss out a couple of other techniques that I found useful over the years and that indeed we use. So technique that I'll talk about now is called XZ, which is exchange spectroscopy. And what this is useful for doing is identifying conformers or other species in moderately slow exchange. A situation comes up where you'll prepare a compound, let's say a carbamate or an amide, and you'll see other peaks in the NMR spectrum. We saw this with amides. We talked about this with amides where we could see two different rotamers, or we had that very thorny problem where, remember, we had the series of spectra, and we were talking about this being a minor conformer, that 5-page sheet problem. And so the question is, yeah, sure, you say you think it's a conformer, but how do you know? Your advisor says, hey, we can't publish this. Your NMR spectrum isn't pure. We don't know if it's pure. The reviewers are going to say you've made a mess. How do you establish that that mess really is your compound? Exchange spectroscopy is the same pulse sequence as rosy or nosy. In fact, it's just a nosy or rosy spectrum. And the exchange cross peaks are the same sign as the diagonal. I'll show you what I mean.
When you say sign, are you talking about like phasing?
Yep. Yeah. So in a nosy spectrum for a small molecule, the cross peaks are opposite sign to the diagonal. So in the phasing, you have one. You saw this on when you worked up some of your phase-sensitive spectra, and you had sort of the red region and the blue region, right, with the color maps. This is, yeah, exactly, it's phasing. So these will be on the same side as the diagonal. In the nosy spectrum of a small molecule, that's going to be opposite the cross peaks. In a rosy spectrum, that'll be opposite the cross peaks. Now, the trick on this is timing. And there are really two different time scales for NMR spectroscopy. There's the time scale of the, we talked about this when I talked about dynamic NMR. There's the time scale of the uncertainty principle. The time scale of the uncertainty principle is if a proton doesn't stay in a single spin state for more than a few milliseconds, you won't be able to see, well, how can I explain it? If you have two different states, you won't be able to see them as distinct unless you stay in those different states for sort of 10 milliseconds or more. Then you have the time scale of relaxation, which is magnetizations returning to the z-axis, T1 relaxation, or dispersing in the xy plane, T2 relaxation, and that time scale is on the order of seconds. So you have to window your exchange process. So it's faster than 10 milliseconds sort of time scale but slower than second time scale. I like to ballpark things in my mind. So in other words, you have to window that time scale so it is on the order of 100 milliseconds. In other words, if you have an amide that rotates very slowly, remember we talked about time scale and energy barriers and temperature, you have to raise the temperature to get up into that regime of having exchange. Now, a lifetime of 100 milliseconds means an extra 4 hertz peak width. In other words, the peak width at half height becomes 4 hertz wider. And that's very good, because a typical doublet is like 7, 8 hertz. So you can sort of see a doublet normally has 2 sharp lines. You just want to fatten out your peaks so that your peaks are getting a little bit fat. Normally, a sharp line in the NMR is about like 1 hertz, 1.3 hertz. So you want your lines to get just a little bit fatter. So I'll say choose a temperature so that the peaks broaden slightly by a couple of hertz. Two examples. Let's see, what did I do? I think I made them as, I think it was, yeah, I just took, what did I do? I took 2 papers here. So I'll just hand out a couple from my experience. Nothing profound, but very, very useful for us, and I think potentially for you. So one of these, when you get multiple conformers, it is really, really a nightmare, because your spectra get so complicated. So this is a macrocycle that one of my students prepared. The molecule has 4-fold symmetry, but the problem is you have a conformer in which the molecule has 2-fold symmetry. And there are 2 varieties, two identical degenerate versions of that conformer. So in other words, here you see 1 type of resonance. Here you see 2 types of resonances, but then each of those 2 can swap around. And so my student Sang was trying to establish that these were indeed interconverting conformers. So he ran an XE spectrum. He ran, in this case, a rosy spectrum, and just took the phase, the cross peaks the same as the diagonal. And if you just look here, for example, in your 1D spectrum, you're seeing 3 different, let's see, where's a good example? An expansion here. All right, we'll take this region here. In your 1D spectrum, you see a whole set of peaks associated with a side chain with these protons here. And when you expand it, you can see a cross peak corresponding to one exchanging with the other. So basically this exchanging with this, and then, with this, with this, and then another cross peak with this exchanging with this over here. Anyway, the point is you can see all of those conformers interconverting, which is very useful for establishing that they're related. And he chose a temperature for this experiment that was just right for it. The other paper was a similar thing. It was an equilibration among 2 different species where he's looking at homo and heterodimers, and he mixed one enantiomer and another enantiomer, and this was Michael who did this, and saw some new very teeny tiny peaks in the mixture. So this is one enantiomer, the other enantiomer, and he saw these little tiny peaks, and he wanted to establish whether that was a diastereomeric heterodimer. So how do you do that? You can say they're new peaks, but what are they? So you show that they're an exchange. So again, he ran the nosy or rosy sequence and was able to see exchange cross peaks here to show they're an exchange. And you notice he picked his temperature so that his peaks are the peaks are normally sharp, and he warmed it up just a little bit just to make the peaks a little broad. All right, I want to conclude with two other things, again, just to file away in your toolbox. Things that I find useful. So one of these is called diffusion ordered spectroscopy, DOSY. And what it does is it basically uses the second dimension to separate spectra by diffusion coefficient. And hence molecular weight. And the reason you might find it useful is it's useful for mixtures and identifying impurities. And I'll just show you what I'm talking about with an example. And this is an example out of that 200 and more NMR experiments. So this is a DOSY spectrum in your 200 and more NMR spectra of a mixture of two different molecules, butanol and a triethylene glycol in two different solvents. And what you're doing is using pulse field gradients to separate your molecules by diffusion coefficient. Basically, little molecules like water and methanol diffuse rapidly. Big molecules like propylene glycol don't diffuse a lot. So you end up with a subspectrum here. So here's your mixture, and here's the DOSY spectrum. And you end up with a subspectrum at a small diffusion constant for the peaks associated with the triethylene glycol. Another subspectrum, and you can extract out all your spectra, for your butanol, which is smaller. And so you can see all the peaks for your butanol, right? So in this mixture, you've got all these different peaks. You don't know what's what. And you say, wait a second, this methyl group, this methylene here, and that methylene there correspond to the butanol, and then you have your methanol here, and then you have your water here, so you say methanol and water. We just use this in my lab. We use this all the time for looking at self-association of molecules because, for example, tetramers have a diffusion constant that's about 0.6 that of monomers. But we just use this in a way that you might use it very recently. A student of mine, Mandy, had a sample she just could not purify. And we were trying to say, is there something wrong with her chemical, or is this an impurity? She took a DOSY spectrum, and she saw very clearly that the unexpected peaks were a low molecular weight impurity in her molecule. So she knew, OK, it really isn't something the matter with her compound. All right, last point I want to make. All right. Water suppression. And so the techniques that are involved use gradients or other pulses to eliminate H2O. Now, the reason that this is important to eliminate the water peak, let's say, the reason this is important is it allows observation of some NHs. So if, for example, you have, let's say, an alkaloid that has an amide NH group and you want to be able to see that amide NH group, you can take a spectrum in 90-10 H2O D2O, because on the laboratory time scale, that's the third time scale, so we have uncertainty principle, relaxation, laboratory time scale. On the laboratory time scale, if you dissolve an amide in pure D2O, the NHs exchange with deuterium, as do the OHs very quickly, in fact. The NHs exchange with deuterium, and you can't see them. So you can never see protons on a heteroatom in D2O. Never, I won't say never, but you almost can never. So you take the spectrum in water with just a little D2O for the lock. But then the problem is you have 50 molar H2O in your sample. You have 100 molar protons from that, and you need to get rid of it. And you can do it by using gradients to do so. So I will refer you to two things. One is just in your 101 and more NMR spectra, an example of this. They do it on sucrose, which is kind of a lame example because you can never observe OHs, but you're suppressing the region right around the water. But the thing that I will do in conclusion is just give you a handout and one closing comment here. This handout I find very useful. So you're still fighting the uncertainty principle. If your protons are exchanging very rapidly, you will not be able to see them because they will be part of the H2O peak that's suppressed. You have to get the exchange rate down on the order of hundreds of milliseconds or greater. And this happens to be a graph for proteins from a book by Vutrich. And what he points out is as a function of pH, you have your exchange rate here. This graph is a little confusing. This is an exchange per minute. So the line that I've drawn at 10 to the 2 is exchange on the order of 100 per minute. In other words, a lifetime on the order of 500 milliseconds. So in this range, protons like amide protons on backbones can be observed, and in this range up here, they're not observable. What does that mean? That means that you can never observe OH protons. Peptide and other sorts of amide protons can be observed in the acidic pH range, but in the basic pH range, their exchange rate goes fast. So typically, you have to tweak with the pH a little bit. All right, that's, I think, all the sort of final brain dump I wanted to give you of things that I've found useful or think you'll find useful. And I will see you a week from Saturday, if not sooner. Yeah.